First of all, thank you for the invitation to speak to this big group. A very impressive number of people online and associated with your annual meeting. So congratulations on the success of that. And again, especially thank you for the invitation to talk about something that I'm passionate about, and I hope all of you are as well, and that is climate change. It is certainly going to affect the agrologists' world in the coming decades, if it hasn't already. And I hope I leave time at the end to hear about that. I would love to hear your perspectives on the thing that I'm about to say. And what I'm about to say is I'm going to give you an update about the state of the climate. I think you're probably all well informed, but I'm going to remind you about what's going on in the world. And then I'm going to dig down into the conditions that are projected for your fair world, and that is my home province of Saskatchewan. So here we go. I hope to hear some questions from you and some comments at the end, and I hope to leave some time. I'm going to try to stay on time. I have a lot of slides, and I've given permission for this to be recorded and shared. And I've also given permission, or I'm going to give permission to use the PDF of this to share around as needed. So a climate update. As is in the news almost every day, including every day this week, the world is getting a lot warmer. Here's a graph. I'm a graph guy. Get ready for some graphs. Here's a graphic that shows that the world has warmed over 1 degree Celsius over the last 100 years relative to pre-industrial. And in this case, pre-industrial means 1880 to 1920. And last year, 2023, was a record, easily broke the record as the warmest year on record. And we're going back to 1880 only here because this is the time frame in which we have really good instrumental observations around the world to calculate a meaningful average global temperature. And the last 7 months of 2023 were each the warmest on record. And I'm just going to show you some of that. So here's if I get rid of some business here so I can see my own graph. There we go. So here's June. June last year was a record for the world as a whole. So the bar on the right in the histogram here is above the previous record. July was a record, and you might recall that July got a lot of attention last year for some reasons that I'll present here in a second. But July broke easily the record of the warmest July on record. Again, this is for the world as a whole. For us in Winnipeg, maybe not so much in Saskatchewan, according to the data I looked at, but here in Winnipeg, in Manitoba, it was actually a very cool July. But this brings me to point out that what happens locally is not necessarily representative of what's happening globally. The globe, many parts of the globe, as you see in the reds here, were much above normal, or at least above normal. A few places, several places were below normal, and the high plains, the Great Plains adjacent to Manitoba here were particularly cool. And indeed, if I look at a graph of the temperatures of 2023 for Winnipeg, the red dots on the graph are the maximum temperatures recorded every day last year. The blue dots are the minimum temperatures recorded every day. The minimum temperatures in July for us in Winnipeg were 2.1 degrees Celsius below normal. I think much of Saskatchewan was just a fraction of a degree below normal. But of course, that was only 1 month. We recovered from that, if you will. And by the time we got to December, as you well know, it was really warm. December was 7 degrees above normal. It was even higher in parts of Saskatchewan. May, if we go back here just briefly, May was really warm too, and I think it was in Saskatchewan as well. Indeed, May set a couple of really interesting records. The period of May 26th to June 8th of last year, the average maximum temperature was 23.58. Only 8 other 14-day periods in which there was a day in May were warmer than that in the period of record for Winnipeg, which goes back to 1872. So the red dot here is what the average maximum temperature was over those 14 days. No other 14-day period, or only 8 other 14-day periods out of some 5,000 that had a day in May were warmer than that. And even more impressive, perhaps, there were only 94 other 14-day periods at any time of the year from 1872 that had an average temperature higher than it was for those days in May. 55 out of 55,000, we were number 95 last year. These are the kinds of records that are being broken all over the world. Here's Regina. Regina was 0.4 degrees below normal, the minimum temperatures. It was the minimum temperatures that were really odd. And the maximum temperature in December was 8.5 degrees above normal. Very, very unusual events. Swift current, 9.5 degrees above normal, and swift current in December, 0.6 degrees below normal for the minimums in July. And of course, I'm speaking to an audience that knows this very well. We have a crazy amount of variability in our weather in the prairies, and that may even get more so in the coming decades. If we get back to the global trend, August was the record. September was a record, and indeed, look at here, September broke the record for breaking the record. No month had ever broken the previous record by as much as September of 2023 did for the global average temperature. And of course, here we're starting to get, as we did in July, a lot of attention from climatologists and the media, like, what the heck's going on here? These are temperatures that are really unusual. And they certainly were. October was a record. November was a record. December was a record. January was a record. February was a record. And we'll see how March comes out, but I would be very surprised if it's not a record as well. I love to throw these things at you. January 29th to February 7th, those 10 days here in Winnipeg, the minimum temperature was 18.3 degrees above normal. The average minimum temperature was 18.3 degrees above normal. No other 10-day period in Winnipeg's history had minimum temperatures that much above normal out of 55,000. Crazy. Speaking of crazy, here's the daily average global surface air temperature. So this is the globe as a whole, showing for every day of the year over many years, going back to the 1980s, what the temperature was. And as you can see, it peaks in July, and this is because it's dominated by the Northern Hemisphere land temperatures. And the big red line there, the thick red line, is the average daily temperatures last year. And it's, as you can see, it's way above any other previous year on record. And in fact, this part of July, the first few days of July, are ostensibly the warmest days ever, or at least for a very long time. The daily average global temperature on almost every day since last spring has been a record. And the black line, I updated it just a little while ago, the black line is this year, and we're still, for the most part, way above normal compared to all other years, and even the 2023 record. And those went back only to the 1980s. If I go back to the 1940s, we're way above. In 2023 in particular, in the 2020s in general, we're way above what the temperatures were about 80 years or so ago. Long story short, as if you don't know, the globe has been getting warmer. It's been getting a lot warmer. And as you might know too, it's very much in the news these days, and that is it's not just the air that's warmer, it's the ocean that's warmer. And I would argue that this is the more important variable to be make note of. The ocean comprises 70% of the Earth's surface, and the ocean has a lot of mass compared to the air, and when its temperature rises, it means there's a lot of heat involved. And indeed, oceanographers are quite literally shocked at how warm the oceans have been since last spring and continue to be. There was an article distributed on the news services just yesterday or today from the head of NASA's climate branch that says we really don't know why the temperatures are the way that they are. Undoubtedly, the El Nino has something to do with it, and there was a volcanic eruption that might have caused some warming, and a few other things. But climatologists, oceanographers are perplexed at why the temperatures have jumped up and why they continue to remain very high this year. They will likely, or the expectation is that they'll go down as the El Nino fades away, as it is doing. But if they don't, um, uh, Gavin Schmidt, the head of NASA, says then we have something to worry about. Something's changed in the climate system. So stay tuned. The North Atlantic is very warm as well. The ocean is very warm in the North Atlantic, as it is in many parts of the world. And this is worrisome for a lot of reasons, including the upcoming hurricane season. This could be fuel for some really severe hurricanes this year. So I'm just giving you a brief introduction here, but there's just so many indicators in the climate system that it has profoundly changed over the last 100 years, and then quite a bit over even the last year. And of course, this is affecting a lot of things, including people. Last year, virtually no one escaped the heat waves, the heat that we found around the world. 98% of the world's population was exposed to global warming last summer, June, July, and August. Very large, almost everybody was affected by temperatures that were to some degree exacerbated by climate change, according to the attribution scientists. Half the world's population faced extreme heat for at least 30 days last summer. And so it was felt by a lot of people. Over 3.8 billion people, 48% of the global population, experienced at least 30 days last summer when the temperatures were made 3 times more likely to be that high because of climate change. Attribution science kind of pointing the finger, looking for the fingerprint of climate change has become a very important science, and it very much came on board last year. And of course, there are effects. And I should point out that a lot of people suffered, a lot of people died. There were very severe storms and so forth. Don't want to dismiss that. In the physical world, there were big changes. Antarctica had never seen as little ice as it had around Antarctica. Not the ice sheet itself, but the ice that grows around Antarctica, just as the sea ice grows in the Arctic every winter here. They had a record low amount of ice, and it's recovered somewhat, but it's still very, very low compared to normal. And that's worrisome. And then, of course, it's in part because the ocean is really warm, even around Antarctica and under the ice of Antarctica. In the Arctic, it wasn't a record year last year. It was only the fifth lowest. But as you can see, the trend for the amount of sea ice that's left in the ocean in the Arctic at the end of the summer has been getting lower and lower. And as you might know, there are some people, some models that say within 10 years, we may have no ice in the Arctic at the end of the summer, no sea ice at the end of this summer. And that would be a huge change to the global climate system. Just a couple of days ago, the UN's World Meteorological Organization issued its annual State of the Climate report, and they issued a red alert, essentially, trying to get media attention. A red alert, things are really strange. Last year was the warmest year on record, 1.4 degrees, 1.45 degrees above pre-industrial. Ocean content, we've never seen anything like that in the 65 years of observation that we've had really good records of ocean heat content, not just at the surface, but below the surface. 90% of the global ocean experienced heat waves. Global sea level reached a record high. Glacier ice loss around the world was a record. We've never seen that much ice disappear as we did in 2023. Glaciers in Switzerland lost 10% of their mass in the last 2 years. Of course, we know that devastating wildfires occurred in Canada last year, as they did in Europe and Hawaii, you might recall. And extreme heat and intense rainfall in many parts of the world were very newsworthy and unfortunately killed thousands of people, such as was the case in Libya last year. So again, to beat the drum here, things are very strange. Things have changed a lot globally. And again, you can't look out your backyard, you can't look out your window and say, well, no, they haven't changed very much. They've changed around the world in a very big way. And they've changed in your backyard as well. Such that not infrequently, climatologists, scientists issue warnings about what's going on in the world, advising, of course, we should get on with trying to reduce the impacts and the changes. And there's a lot of people, including Gavin Schmidt, the head of NASA, saying we may be moving into uncharted territory. That is the kind of changes that we saw in 2023 and in some recent years as well. They say we are entering an unfamiliar domain regarding our climate crisis, and it really is a crisis, a situation no one has ever witnessed firsthand in the history of humanity, an enormous amount of change. And of course, we should ask and probably know, why is this happening? Quite simply, it's because more energy is entering the planet system than is leaving the planet system. The planet has sunlight coming in, and in order to maintain a constant temperature, it has to release infrared radiation. It's not doing that as much anymore, or at least it's unbalanced. It, it we don't have time here to talk about energy balances, but sunlight comes in, some of it gets reflected off the clouds and the surface, some of it gets absorbed a little bit in the atmosphere, a lot of it gets absorbed at the surface, and then the surface warms the atmosphere. Essentially, the atmosphere is warm from below, but the energy, the long wave radiation, the infrared radiation that we are emitting, the planet, you and me, everything around you is emitting infrared radiation. A lot of that is prevented from getting to outer space because of the greenhouse gases getting in the way. Greenhouse gases are good at absorbing infrared radiation. They're not good at absorbing sunlight, and they send some of that energy back. And the more greenhouse gases we have in the atmosphere, the more is sent back. And that's why the system warms up. Or that's one way that the system could warm up. It could be, as some people still like to cling to, this notion that maybe the sun is brighter. No, it's not. The sun is not always doesn't always have a constant brightness. The irradiance of the sun varies. It varies in particular because of the sunspot cycle. Here's today's image of the sunspots on the sun. The number of sunspots varies over time, as you'll see, and as you might know. When there are lots of sunspots, the sun is a little bit brighter. The spots themselves are actually cool, but around the spots, around those dark spots that you see on the sun there, it's really bright. It doesn't show up on these particular images, but they're called faculae around those spots, and light energy is pouring out of those faculae more so than there's cooling associated with the sunspot. And what that means is that when there's lots of sunspots, and on the bottom graph here, we have, since the 1970s, the number of sunspots. It goes up and it goes down according to the sunspot cycle. And that corresponds with the brightness of the sun, the irradiance of the sun. It's not much of a difference. It's a very small amount of difference, but there actually is variation in the solar constant. It's not constant. We are currently nearing the peak of the current cycle. The last couple cycles have been lower than before, and some people were projecting we're about to go into a period where the sun is dim. That's very, very unlikely, but this variation isn't very great, but it cannot explain global warming because I don't see a big trend in the solar irradiance here, and we have data going back for a long period of time. It just does not match the temperature changes that I showed you earlier in those graphs. The physics of it doesn't make sense. The visual aspect of it doesn't make sense. Yes, the sun is not always the same brightness, but it's not getting brighter to cause global warming. It's just not. So if there's not more sunlight coming in, it must mean there's less Earth light going out. And that is exactly what's happening. And the way that we measure that is with the concept of radiative forcing. It's in watts per square meter. We measure the intensity of the radiation. And essentially what we're showing is, are there things that are causing more radiation to stay in the climate system or to block radiation from coming into the climate system? And yes, there are many things, and here they're summarized. The things things above zero are things, driving forces that cause the planet to get warmer by having more radiation stay. The things that are on the bottom cause more radiation to stay out. And the number, as you can see, perhaps these spiky lines, those are volcanoes. When we have big volcanoes, such as we did with Pinatubo and Krakatoa and Tambora and Mount Agung and so forth, they temporarily block out sunlight because those aerosols reflect solar radiation. The Earth gets a little bit cooler, but only for a little while because the aerosols precipitate out, the atmosphere clears up, and the sunlight comes through again. The blue line here is tropospheric aerosols, which is essentially a pollution from our industrial activities and burning of fossil fuels and so forth, and also combined with surface albedo. And principally, that's land use change. If we cut down a forest, the ground isn't as dark, it's brighter, and it reflects sunlight. And so deforestation tends to cool the planet, whereas tropospheric aerosols. The troposphere is the lower part of the atmosphere. Aerosols put into the troposphere also block out sunlight. So we've actually had a negative impact on radiative forcing human activity, but we've also had a lot of positive forcing, if you will. There's the solar. The solar is a very bit player in all of this. It really just kind of wiggles around, doesn't really change very much. It's the green line and the purple line that are important. The green line is the greenhouse gas forcing caused by those greenhouse gases, carbon dioxide, methane, nitrous oxide, and fluorocarbons and their related compounds that we put into the atmosphere. That's the total radiative forcing. And the purple line is the radiative forcing only associated with carbon dioxide. And this is why we're obsessed with carbon dioxide. Carbon dioxide is by far the most important positive radiative forcing agent. It's causing more radiations to stay in the climate system, not escape to outer space that would otherwise help to cool the planet. So try to create an equalized temperature. Carbon dioxide is by far the number one radiative forcing agent. And the warming associated with carbon dioxide then triggers other changes. For example, a warmer atmosphere can hold more water vapor. Water vapor is the most important greenhouse gas, but it's carbon dioxide that we're changing the concentration of, and it in turn changes the concentration of water vapor. And so we get positive feedback. So there's a doubling down, if you will, caused by carbon dioxide. Here are a couple more things about how we're changing the planet on a big way, and then we'll drill down to us. The amount of sunlight absorbed by the planet is increasing. Satellites have definitely detected that there's more sunlight being absorbed at the surface, and that means there's more energy entering the system, which has to be shed. So even though the sun may not be brighter, the more the sunlight is being absorbed because the surface is getting darker. One reason it's getting darker, of course, is we're seeing less and less sea ice. We're seeing less and less ice around the world. Ice is good at reflecting solar radiation, and that means that contributes to warming at the surface. Another interesting thing that might be a cause for why 2023 was so warm and continues to be so warm in 2024 is of new regulations that were passed in the shipping industry around the world. And shipping, of course, as you know, is a really important means by which our goods are shuffled around the world, our globalized economy. For a long period of time, ships have been very, very polluting to the atmosphere. They burn dirty diesel fuel. The diesel engines use sulfur-laden fuel, cheap, not very refined fuel. That means sulfur comes out of the smokestacks of those ships going all over the world. And that sulfur is not very good for human health and ecosystem health. And so in 2020, they started to phase in regulations about cleaner fuel being required. And they really kicked in over the last couple of years. And therefore, there's a lot less pollution in the atmosphere from these ships. And it's producing a marked increase in sunlight getting to the surface. It's not being blocked out by the aerosols and the clouds that are formed behind the stacks of these ships, thousands of ships every day. We've actually done a good thing. We've cleaned up the air, but it's actually allowing more radiation to get to the surface to warm us up, which is enhancing global warming. And finally, the Earth's energy balance is definitely not balanced. There's very good evidence from satellite imagery that there's more energy staying in than is going out compared to the past. And this is measured in watts per square meter. A watt is a joule per second, a square meter is a square meter. So on average, according to the red line here, the average over these years, 1.35 extra watts per square meter for the planet as a whole. An extra joule, 1.35 extra joules of energy every second for every square meter of the Earth. That doesn't sound like very much, but it is. And I'm going to show you something here, and I'll let you look at this later on in the recording or in the PDF if you look at it. But here's an exercise I do with my students. How much energy actually is that? Or let's kind of try to put that into perspective. So here I'm trying to put into perspective 1 extra watt per square meter, 1 extra joule every second for every square meter of the Earth continually. And so if you calculate how much this is, it's actually the equivalent of all of us around on Earth all 8 billion of us, running 40 Dyson hair dryers at high max continually. That's 318 million, if I'm looking at that right, 318 billion Dyson hair dryers, 1600-watt hair dryers, 318 billion Dyson hair dryers running continuously. That's how much energy is associated with 1 extra watt per square meter. We're at 1.35 and going higher. It's a lot of energy. It's also equivalent to 702 Hiroshima bombs blowing up every day. That's how much energy that is. It's crazy. Small numbers can mean big changes. So our future is my conclusion, or I hope you see that too. Our future is determined by emissions, largely of carbon dioxide. And of course, that carbon dioxide comes from us burning of fossil fuels. Fossil fuel use has increased a huge amount since the beginning of the Industrial Revolution in 1750. And here we have a breakdown of coal in black, oil in orange, red is gas. The gray here is cement production. The production of cement for making concrete is very damaging to the atmosphere. It takes a lot of energy to make cement, and we usually burn fossil fuels to make that energy. And the chemical reaction that goes on in making that cement releases carbon dioxide. So because we use so much concrete around the world, cement, it actually shows up as an important player in the concentration of carbon dioxide in the atmosphere released from human activity. And then there's gas flaring, the rogue methane typically coming out of smokestacks and refineries, such as we see all over the place. 36 billion tons of carbon dioxide per year. That's what humanity is now emitting into the atmosphere, 36 billion tons. 40% of all the emissions emitted by humans since the beginning of the Industrial Revolution back in England, 40% have occurred since the year 2000. 40% of all the carbon dioxide emissions from fossil fuel burning in industry have been released since 2000, 54% since 1990, 66% since 1980, 76% since 1970. So the graph here is showing that the Industrial Revolution didn't have very much of an impact until the 1800s, then it picked up in the 1900s, and then post World War II, it just went crazy. And we benefited from this, of course, from the burning of fossil fuels and industrialization. Many people around the world have good lifestyles and health and happiness and so forth, thanks to fossil fuels, but it comes at a cost. And that just can't be allowed to go on for very much longer, or else we're going to have really significant negative consequences. Canada is a relatively small player. The emissions coming from Canada really didn't pick up until the 1800s, and we currently emit about 2% of the world's emissions directly. But that doesn't count the emissions that come from the oil and gas that we sell to other countries around the world. Our footprint is much larger than 2%. And that's why we kind of have an obligation to change things. Thank goodness, all that carbon dioxide, 36 billion tons that's added to the atmosphere every year, doesn't stay in the atmosphere. Only half of it stays in the atmosphere. About a third of it ends up being soaked up by plants and soils of the sort that you like to take care of. And about a quarter ends up in the oceans. Furthermore, 90% of the heat created by global warming, if you will, ends up in the oceans. The oceans are not absorbing carbon dioxide, they're absorbing the heat and storing it, at least temporarily, in the oceans. Pointed out earlier, the oceans are getting warmer and warmer and warmer. That heat is just temporarily in the ocean. It will eventually come out of the oceans. So even if we stop carbon dioxide emissions and slow down global warming, there's heat that's going to ooze, if you will, be emitted by the oceans to counter all the kind of good things that we are doing. So there's, as they say, there's a lot of heat in the pipeline. The ocean is the reservoir that's storing heat temporarily. It'll come back into the atmosphere later on. Consequently, of all these emissions, the carbon dioxide concentration in the atmosphere has been increasing. So here's a graph going back to the 1750s. For the longest time, and in fact for about 1 million years, it's not gone not gone above about 280 parts per million. Parts per million, you're generally scientifically oriented people. It means you take a million molecules, on average, 280 of them are carbon dioxide. It's a trace gas. 280 out of a million isn't very much. If somebody won $1 million and they gave your share 280, you'd be ticked off. That's not very much. It's a true trace gas, but it's disproportionately important in the climate system. There's my dear old dad, who was born in Indian Head in 1922. When he was born, the carbon dioxide concentration for the world was 303 parts per million. So it had started to increase because of industrialization. My mom, who's still alive in Regina, was born in Yellowgrass in 1933. It was 307 parts per million when she was born. Skip ahead to me being a little nerd in Regina with a couple of ducks for a science experiment for some reason. I don't recall. It was 324 by 1969. And in 2017, when I met my lovely partner, Laurel, there's our crazy dog, Benny, it was up to 407 in 2017. And now it's over 420. Every year it goes up by 2 or 3%, parts per million, pardon me, thank goodness, not percent, 2 or 3 parts per million. So the carbon dioxide concentration of the atmosphere is about 33% higher than it was when I was born in 1957. It's about 50% more than it was at the beginning of the Industrial Revolution, and it continues to tick up, tick, 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 and it very much is like a bomb. So the question is about our future climate, including the future climate of Saskatchewan, is how high is that Keeling curve? That graph of the carbon dioxide is called the Keeling curve. How high is it going to go? Well, it really depends upon us. Are we going to collectively get away from fossil fuels as fast as we can? Are we going to go really green, solar? Are we going to go nuclear? What's the population going to be in the future? How many people are going to be using energy? And so many human decisions determine how much carbon dioxide and other greenhouse gases we have to add to the atmosphere. And so if we want to project what the future is going to be like, using climate models, which is the only way we can figure this out, these amazing supercomputer-driven climate models, we need to put in different scenarios. For example, the 8.5 scenario here is the one that says we essentially don't change. So 36 billion tons every year or even more. And the orange scenario here is such that right now we rapidly start to decline our carbon emissions by switching to alternative fuels and conserving energy and so forth. It depends upon the trajectory of carbon emissions, about the trajectory of the temperatures. And so different scenarios are used in climate models to figure out what if, the projections. And what they say, on average, these suite of climate models that are around the world, if we follow that high carbon scenario, which we likely will not, let's hope not, that would mean 3 more degrees of warming by the end of the century. We've already warmed a degree, and all the changes you could think about climate change, melting of glaciers, acidification of the ocean, heating of the oceans, storms, droughts, floods, wildfires, all that's only with 1 degree of warming. Think about another 3 degrees of warming. It's just unthinkable. If we follow the lower carbon scenario, we'll call it the low carbon scenario, it's still not very low. That's only about 2 degrees more warming, or a little bit more than that, actually, by the end of the century. And this is relative to 1850 to 1900, as you can see. One way or another, there's a lot more warming coming. Let's hope it's the lesser amount of warming rather than the higher amounts of warming, and that will affect us. And in particular, because Canada feels global warming at twice the global rate. A lot of people don't know this. If the world warms up by 4 degrees, Canada warms up by 8 degrees on average. The Arctic warms up by triple the global warming value. So the temperature changes associated being observed and going to be observed in Canada are about double the rate of the global rate of warming on average, and triple the amount in the Arctic. And that's definitely observable. The amount of sea ice that's disappearing in the Arctic is a result of the warming being concentrated in the Arctic, much more so than in many parts, if not all parts of the world. And that will continue. And of course, it's it's having major implications to transportation, culture, resource management, biodiversity. There's some positives, of course, with some of this, but in the long run, it's negative. The reason why a small change in the temperature, or especially a large change in the temperature, is problematic is that if you shift the normal curve to the right to indicate a small change in temperature, it creates a disproportionate increase in the high temperatures. So if you define high temperatures as 30 degrees, under the old climate, you'll have this pink area as indicating the frequency of high temperatures. Under the new temperatures, with the shifted to the right curve, you get a lot more of those hot temperatures. And that's, of course, is exactly what we're seeing. We're seeing lots of high temperature records. We're seeing a lot less cold temperatures. We still get cold temperatures. It was minus 45 in Edmonton this winter. 19 days later, it was 11 degrees Celsius. I'm sure you had some really cold temperatures in Saskatchewan, as we did, although we did at minus 40 in the south here. This is all indicative of these more hot temperatures and fewer cold temperatures is indicative of the shift to the right of the means in the distribution. And coming with those high temperature changes is more water vapor in the atmosphere. For every degree of Celsius temperature rise in the atmosphere, it can hold 7% more water vapor. 7% more water for a 1 degree Celsius change. And that translates into more potential for rain. And we're seeing more intense rainfalls in all kinds of systems around the world, including in Canada, including in the prairies. I'm just going to skip over a couple of things here. So let's get down to the projected temperatures for our part of the world. And I refer here to our Climate Atlas of Canada. This is our flagship product at the Prairie Climate Center. It's been around for, version 2 was released a couple years ago, and we're going to release a version 3 this summer, I hope, using the latest climate model data. Right now, we're using the previous generation of climate data using RCPs. Anyway, and so you can. I hope all of you have been to it, and hope all of you will go to it. We get about 170,000 hits a year, and get a lot of good attention. It's not just an atlas. We have videos. We have lots of videos talking to real people. Would love to talk to an agrologist about their perspective on climate change. Get you on camera. We have at the Climate Center, we have 2 professional filmmakers. We have a staff of about 8 people, full-time staff members. We rely upon external funding from the federal government, from Public Health Agency of Canada in particular right now funds us. The province of Manitoba is providing us with some contract money. Infrastructure Canada, we have a big project with Infrastructure Canada to provide guidance for First Nations around Canada about how they need to adapt or how they could adapt to climate change. Anyway, we're a going concern, very proud of what we're able to do and the attention we get and the work that's being done using our data. So you can click on anywhere in Canada, including my hometown, Regina, and we'll tell you what the climate models say. Under the high carbon scenario that I mentioned, kind of that worst case scenario, I hope it's worst case, and under that lower carbon scenario, the orange one, which is still way too high, but better than the 8.5, better than the high carbon scenario. And here are the kinds of things that we show for all these places. And indeed, it's not just cities. We have 497 place names and 600 Indigenous communities around Canada or so. We've indigenized the atlas using proper Indigenous names, respectful names, how these communities refer to themselves. And so you can click on and any grid square. These are all map squares all across Canada, and we'll show you graphical representations of what the projections say under the low carbon scenario and under the high carbon scenario in the near future and the farther future. Near future is 2021 to 2050. Farther future is 2051 to 2080. And we also provide the annual data, and we do it for using 24 different models. We don't know which model is correct, so we hedge our bets, if you will. We use 24 models and take the average. This is the standard practice in climatology. So let's quickly go through here. Here's the message is essentially the same all across southern Saskatchewan. So if I just throw a few stations here, I assure you when you go play around with the atlas, you'll see that the message is about the same. Annual number of days above 30 under the low carbon scenario, we go from recently 18 days to 40 days in 2051, 80, that 30-year period, and higher beyond that. 18 to 40 under the low carbon scenario. Under the high carbon scenario, 18 to 54. And that's about the same in Winnipeg as well. Instead of having just a couple weeks of plus 30 in an average year, you go to have 7 or 8 weeks of plus 30 as you approach the end of this century. Big changes, 36 more days of high temperatures, which has, of course, implications for growing conditions and so many other things, including human health and safety. The annual number of days of minus 30 is crashing. Every year is different. We still get minus 30s, but a lot less than we used to. Under the low carbon scenario, Regina will maybe go down to 4 from 12 or so. And, oh, pardon me. And under the high carbon scenario, we go from 12 to about 2. So not much of a difference there. We're losing those cold days. And again, there's some benefits to that from an energy use point of view, from a health point of view, but there's also consequences in terms of pest management and hydrology and so many other things. I'm just going to skip forward and get to the frost-free season. I hope I chose this variable as something you would be interested in. Under the low carbon scenario, Regina, indicative of southern Saskatchewan, goes from 123 days or so. This is model data, not observed data, but it's close to the observed. 123 days recently to 146. 3 more weeks of frost-free season under the low carbon scenario. Under the high carbon scenario, 33 more days as we approach the end of the century compared to recently. That's good news for agriculture, right? You can grow more things, but there are costs to having a longer growing season from a weed point of view, from a pest point of view, from a water point of view. But there definitely are some benefits. Saskatoon is about the same, and so forth. And I'll just race through this, but here's an interesting way to look at how big the changes are that may be coming for places across the prairies. I was the guest editor for the Prairie Garden last year, or the year before actually, the 2023 issue, and I wrote an article that presented this data, and it's data that shows who now in the United States has the climate that we're projected to have in the future under the low carbon scenario and high carbon scenario. So I went and grabbed Regina's images. These are all online. And so here's the winter temperatures. These take a little bit of interpretation. So each of these color codes here is a different 15-year period. The red ones are the farthest ones in the future. And so let's concentrate on those. So in the year 2081 to 2095, under the low carbon scenario, Regina is projected to have the winter temperatures, winter average maximum temperatures in the winter that these red dots currently have. So these places in South Dakota, for example, currently have, according to observed weather data from the United States, currently have the temperatures that Regina is expected to have in 2081 to 2095. That may not seem like very much of a distance here, but as I think a lot of you know, you don't have to go very far south in the wintertime to find the winters are a lot warmer. And if we go to the high carbon scenario, it's further south. That is, we start to have the winters that even more southerly places in the United States have. And there's some benefits, of course, to that, as I just pointed out. In the summertime, the distances are greater because of the temperature gradients being different. So here are the average maximum temperatures in the summer under the low carbon scenario. So Regina will have is projected to have, we don't know what will happen, projected to have the winter summer maximum temperatures that these red dots currently have. And if we go into the high carbon scenario, we go way down into Kansas. These are places that currently have the summer maximum temperatures that Regina is projected to have in 2081, 2095. Essentially what this means is the climates of the United States are marching towards us, especially under the high carbon scenario. They'll march a long ways. And I think a lot of you know that the summers and the winters in these American places south of us are a lot different than we have. Kansas, Oklahoma, these places get very, very high temperatures and dozens of high temperature days of the sort that we only get a couple dozen of in an average year. Um, here's Saskatoon. Here's Estevan. Estevan being close to the border, of course. You're down into Oklahoma for summer maximum temperatures under the high carbon scenario, to be a bit dramatic, to show the high carbon. That's summer, July maximum temperatures that are 7 degrees above what they have been recently. Precipitation, here's a big message, of course. Precipitation is generally expected to get higher. There's more energy in the atmosphere. There's more water vapor in the atmosphere. Generally, all months of the year get wetter. Here we're looking at the Regina monthly precipitation under the low carbon, the light blue, and the darker blue, and generally they're higher, except in July and August. And if we go, that's 2021 to 2050, the current 30-year period that we're in. If we go to 2051 to 2080, we see even wetter conditions under the high carbon scenario and drier conditions in July and August. And if we go to Saskatoon, we see the same thing, wetter in all times of the year, except on average, every year is different. That's our crazy climate, except in July and August. The current, except in July and August, especially under the farther scenario. Estevan, July and August drier. And generally, that's what's seen in our maps. The brown indicates for July in the far future, under the high carbon scenario, the southern part of Canada gets drier in the summertime compared to now, a little bit, and the north gets wetter. And so I'm looking at my watch here, I've got 12 more minutes. So a fair question to ask, is this really happening? Yes, it is. And so if I look at observed data from actual weather stations, not projected or modeled, there's a lot of change. The problem is, of course, that the observed weather data in the prairies is just so noisy. We have such enormous standard deviations of the precipitation of the temperatures from year to year. There's a lot of noise that can distort the signal. But here's a good signal. These are the average January minimum temperatures in Regina going back to 1884. I've smooshed together 25 different weather stations that are within 50 kilometers of Regina. And of course, incredible amounts of variation in the January temperatures. And but there is a signal. If we look at this statistically, definitely in the last 50 years in particular, there's a signal. We're seeing a lot less of this really cold stuff and slowly but surely more of that warm stuff in January. The red line is the projections as a smooth version of the projections for the high carbon and the low carbon. Somewhere in here is where we're headed, probably in between them. I hope it's at least in between them. Here's Regina's minimum temperatures in the wintertime. I grew up in Regina in the 60s and 70s and I guess the 80s. It's true that I remember a lot more cold weather in Regina winters and Saskatchewan winters and Manitoba winters. They're getting warmer and warmer. You can still have bitterly cold weather events, but on average, as was the case this year, exacerbated by El Nino, we had a really warm winter in Winnipeg and so to do in much of Saskatchewan. Anyway, I'm going to zip through these and get to the conclusion so I can perhaps answer some questions and get your comments. So the implications for agriculture and the kind of world that you live in and resource managers live in, there's some positive aspects to ongoing changes. Longer growing season, less stressful winters from a temperature point of view, a more abundant precipitation, at least for part of the year, especially in the long run, things get wetter. Longer growing season, opportunity to grow new crops, opportunity to get higher yields. There's more carbon dioxide in the air. That's good for a lot of the plants, of course, as long as they have nutrients and water. Lower winter heating costs, fewer extreme cold events. There's some good news in there, but it's countered, unfortunately, by the negative implications. Increased risk in the coming decades, exposure to floods, those intense precipitation events. The droughts that we've experienced, unfortunately, in recent years are likely to become much more frequent. Even if the precipitation goes up, or if it doesn't change very much, those temperatures are going to suck the moisture out of the ground. Intense rainfall events, more variability and instability, and we've seen some of that playing out over the last recent years. This is, of course, a challenge for water management, and hopefully we're getting into the mode where we're going to store water more frequently than we did in the past, than we even do now for those dry periods. And of course, keep that carbon and the nutrients in the soil. Soil management will become a real challenge and important. So I ask you, in wrapping up my comments, what are you seeing there? I would love to hear some of you say what you're seeing, or does it match with what these projections are about? And therefore, I thank you for your attention, and I'll turn it back over and unshare my screen here and hopefully have some questions to answer. Thank you very much for your attention.
Thank you. Thank you, Danny. It was a great presentation. We did have a few questions come through here.
Great.
So I will, we have less Henrys, but I might save that one for last. I think it'll be interesting. We have one here. Do you have any thoughts on global population strategies? And if you do, how might they be successful with the interconnecting economic impacts? It's a pretty deep question to start off with.
Yeah, that is, I'm not a demographer, but we're just passing 8 billion people for the globe as a whole, and the number of people clearly has something to say about what the emissions are and what the resource consumption is. It's going to continue to go up, but it's likely to level off more than we thought. As to how population control, that's a big question. How do you control the population? You're impinging on human rights. As a lot of you might know, many of the nations around the world have negative population growth. The number of babies isn't replacing the number of people who die. Japan has a crisis. China has a crisis. United States has, not modest growth. Canada has modest growth, but Scandinavian countries, they're losing people um, to death more so than is being replaced by birth. Of course, one of the solutions to that is migration, and we're seeing that as a very important issue, a little bit contentious issue. But we need immigrants to replace the people that we're not replacing ourselves for job growth and so forth. It's a real can of worms, of course, but population definitely has something to say about where we go with regard to emissions and resource use or abuse.
Thank you. Another one from Christine says, when you talk about heat will be released from the oceans later and have an impact, can you speak a bit about what that process is and what the effect looks like?
Sure. Good question. So the top of the ocean is in contact with it's absorbing solar radiation from the sun, and it's absorbing radiation heat, sensible heat from the air. And then that ocean being fluid, it circulates. So a lot of the heat that's captured at the surface goes to deep layers. And there's something you might know called the thermohaline circulation. The ocean has a big circulation, just like the atmosphere does, jet streams and so forth. The ocean takes heat and whatever's in the water and transports it to the bottom of the ocean much slower, of course, because water is denser, and it goes to the bottom of the ocean, and it goes along the bottom of the oceans, and it resurfaces near the equator, it resurfaces near the Antarctica, and it goes into the Pacific, and it comes up again. So there's this big four-dimensional circulation of water and heat and salt and nutrients in general in the ocean. So a lot of heat is being taken to the bottom of the ocean that will eventually come back slowly. It takes decades to centuries for that heat to come back up, but eventually it will. So even if we really get drastically serious about reducing heat content in the atmosphere in the near term, there's heat that's going to come back in the pipeline, as I said, to come back to counter or to add to heat that we may have prevented by controlling emissions or whatever. It's a very, very complicated three-dimensional, four-dimensional system, but there is an enormous amount of heat below the surface that will eventually come back to the surface. It takes a lot of thinking about that and some diagrams. I wish I had more time to talk to you about that. The thermohaline circulation, as you might know, is actually still slowing down. It's getting some press. The circulation in the Atlantic is slowing down. The North Atlantic is a really important part of the global climate system. Cold, salty water sinks to the bottom of the ocean, and that it strengthens the Gulf Stream. So the warm water from the Gulf of Mexico and the Caribbean heads up towards Europe and keeps Europe warmer. That's slowing down, and it may actually stop in the decades ahead. One more thing to worry about. Next question.
Perfect. Have one come in here from Mr. Dave Cubbin. Good to see you, Dave, online. Presentations that I've seen do not talk much about evapotranspiration that goes along with higher temperatures. Could you comment
Mhm.
on this?
I wish I had my fingers on good evapotranspiration data. Evapotranspiration is very difficult to model. You need detailed weather data. All we have at the Climate Center is daily maximum and minimum temperatures and precipitation in our modeling data. We have 22 terabytes of data, but we're not able to directly measure evapotranspiration or estimate evapotranspiration. The global climate models do. We only have a subset of the global climate model data. ClimateData.ca, the federal portal of climate change, they do some estimates of evapotranspiration. And I think it's generally the case that evapotranspiration is being shown to increase, but it's a very, very noisy signal. It depends upon the wind, depends upon the solar radiation, depends upon the precipitation, depends upon the vegetation, and so forth. So evapotranspiration, a very, very important variable to your world, I'm sure, if I'm interpreting your world correctly. It's a really important variable, and I wish we had better data about it to portray. But generally, the assumption is, as you heard, that evapotranspiration will increase because the temperatures are so high at that surface. It gets so warm, it will transpire more so than is replaced by even the enhanced precipitation. Especially during July and August, when precipitation may go down, the temperatures are guaranteed to go up. The thing we're most confident about is temperature change. We're less confident about the precipitation changes. Precipitation is so much more noisy than temperature, of course. But generally, it should go up, the evapotranspiration, and create a greater risk of drought.
We have a lot of great questions coming in here, and some of them I think maybe would require potentially an email and discussion with yourself, Danny. So I do want to maybe just end it off with an interesting question, and hopefully it works out here. But
Lay it
Mr.
on me.
Les Henry, did you overlap at the University of Winnipeg with Tim Ball? If so, what discussions did you have?
We didn't have discussions; we had fights.
I
Uh, yeah, Tim Ball, may rest in peace. He died a couple of years ago, I believe. I think a couple of Decembers ago. He died in Victoria, where he moved after he retired from the university here. He left in 1996, so we definitely overlapped. I used to teach climatology courses with Tim, and Tim had and especially over time, he developed a very different perspective upon this. He didn't believe in global warming. He thought it was a conspiracy. He just didn't believe the science and the models. So he was an outlier in the scientific community from that perspective. And so, as much as Tim helped me get the job in 1987 here, and we were friends. And he was a very good historical geographer, looking at the Hudson Bay Company archives for information about the past, the climate of the past, the weather of the past. That was his forte. But we certainly did not agree about the human role in changing the climate. And so it was a challenging time. It was a stressful time for both of us, I'm sure. But as I say, may you rest in peace.
Thank you for that, Danny. Again, I'm not sure if we're gonna get the questions to you or what, but I do think there
Yep,
are some worth. If I didn't ask your questions, I'm sorry, and we can definitely get you an email for Danny and make sure if those questions are burning, they are answered because, like I said, there were a lot of great ones that we just couldn't get to.
that'd be fine. That'd be fine. Climateguy@gmail.com.
Perfect, easy.